Hello, everyone. My name is Pengbin Tang. I'm a postdoc at Computational Design Lab at ETH Zurich. And today I would talk about a little bit different topic with computational design of metamaterials. Okay, so outline for today. I will first give an introduction to computational design of metamaterials and what is metamaterials and design challenges. And after that, I will describe several computational models to forward simulate these metamaterials. And based on this simulation data, we can then use numerical homogenization to obtain macro-mechanical properties of metamaterial. After that, I will describe one of my recent work for the characterization of macro-mechanical behavior of discrete interlocking materials. And after knowing how to forward simulate and homogenize metamaterials, and there comes to a question of how to inverse design metamaterial with desired macro-mechanical properties. And I will introduce several numerical methods used in the inverse design. And finally, I will talk about the recent research trend in the inverse design of metamaterials. Okay, so let's start. Nature holds infinite examples of materials with exceptional flexibility, strength, and durability. Trabecular structure of bone can provide good balance of strength and netness. The venation pattern of dragonfly wing provides perfect strength, flexibility, and aerodynamic performance. And the pangolin scale skin provides optimum flexibility and protection. And all of these organic materials continue to inspire material and mechanical engineering to build new materials. So first off, what is metamaterial? First, a material are not only defined by the composition, but also the small-scale structure. And the metamaterials are engineered materials designed to have properties that's not found in nature. And they can exhibit unusual properties in response to environmental stimuli, for example, light and temperature. And today I will mainly focus on designing mechanical metamaterials. And the mechanical metamaterials is a subtype of metamaterials that exhibits unusual mechanical behavior due to the internal architecture as shown here. And it allows for various macro material properties with a single material. And for example, high stiffness to weight ratio, high durability, high energy absorption, and negative Poisson's ratio. And this metamaterial can be used in diverse applications. For example, soft robotic hand for grasping via pneumatic and cable actuations. And for example, smart wearables for exoskeleton and sportswear. However, designing metamaterial is still a non-trivial problem. First of all, metamaterial are characterized by large deformation, nonlinearity, strong anisotropy, contact, and other inherent nonlinear phenomena that's, first of all, very hard to predict and characterize. And when considering the inverse design parameters such as structure geometry have a nonlinear effect on material performance. In addition, these parameters can combine into a very high-dimensional design space that is very hard to use trial and error method to explore the design space. So in order to do this, we first need to forward predict the behavior of metamaterials. And so let's come to our first part, computational model. And the metamaterials are composed of different structures, as shown here, such as rigid elements, continuum media, and the elastic rods network. And in order to characterize and design these metamaterials, we need to first simulate the static equilibrium and specified boundary conditions to predict the behavior. And so in this course, I will briefly cover rigid body, finite elements, and discrete elastic rods. For rigid body, we compute the static equilibrium by solving the following unconstrained minimization problem. And here we have the external force, which comes from the boundary condition that we apply to deform the metamaterials. And the other side is the contact or collision force that will balance the external force. And here we have the rigid body transformation Q which contains two parts, translation and rotation. And for rigid body contact, we first have to know the vertex positions. And we can use rigid body transformation to obtain it. And here, the rotation, it comes from Euler vector. We can reconstruct it by using Rodriguez rotation formula as shown here. Okay, after knowing the vertex positions of transformed mesh, we can compute distance between them. For two primitives as shown here, a point and a triangle, we can compute the distance very simply. And for contact, if the distance between two primitives is smaller than the head, then we can treat it under contact. And then we can use a recent state-of-the-art method for contact, which is called incremental potential contact, to compute contact energy. And here, this K, this kappa is the adaptive stiffness, and this B is the barrier potential. And this barrier potential is basically if we have a distance that's getting smaller and smaller, it will return barrier potential until infinity. And then we can solve the unconstrained minimization problems via Newton's method. And for Newton's method, we can start from an initial guess, Q0, and for each reiteration, we compute the gradient and Hessian of the total potential. And with this gradient and Hessian, we can solve linear system to get the search direction. And for rigid body, there is one more thing that we need to do is that we need to somehow guarantee the search direction. Within the search direction, there's no contact or intersection at all. So we have to compute the intersection-free step size while continuous collision detection. And it's a very standard method, usually in triangle mesh. And then we can use the traditional backtracking line search to find the energy decreasing line search step size alpha. And if we find appropriate line search step size, then we can update the configuration to the next step. Okay, that's all for the rigid body dynamics. I only cover the static equilibrium here. And then for deformable solid medium, the finite element method is the usual way to simulate the deformation. And to do this, we start from undeformed states described by x bar, and its deformed states by x. And the displacement u describe how it deforms from undeformed to deformed states. To measure how large is the deformation, let's consider two material points, x1 bar and x2 bar, and the corresponding d vector that gives the data translation. And this d is supposed to be infinitely small. And the deformed vector d for the rest states, for the deformed states, can be represented by using the rest states with translation vectors as shown here. And here we can compute this x2 bar minus x1 bar as using the rest translation vector d bar. And the displacement of x2 bar and can be represented at the position of x1. So we get this following form. Then with the Taylor expansion, we can approximate the above term to the bottom one, and finally we arrive at this form. And here this I plus the gradient of translation vector lambda u is called deformation gradient. Okay, and this deformation gradient basically maps from undeformed vector to deformed vector. And alternatively, we can also write this deformation gradient as dx bar. And So now if we measure change in squared length, we can obtain the midterm, which is gradient f transpose f minus I. And this part is basically the green string, which has this right side quadratic term. And if we neglect this quadratic term, we arrive to this linear cursive string. Okay, so now we know the basic idea of deformation gradient and string. And for simulating a given mesh in 2D and 3D, we first need to divide the input model into elements. For example, linear segments in 1D, triangle in 2D, and tetrahedron in 3D. And for simulating deformable solid, we use finite element to approximate the displacement field and the external loads. Since the displacement field can be complex, the finite element approximation is basically use simple and known functions, which called basis functions, to make the problem solvable. So for a 4D, for 4-node tetrahedron, as shown here, it has 4 linear basis functions. And each basis functions is linear, as shown here. And since we want the value at the node to be exact at the corresponding node, so we have each basis function is 1 at its own node and 0 at all other nodes. So we have this basis function equals to the data function. And therefore, we can obtain the coefficients of the basis function by solving the following linear system. Here is an example for solving coefficients of basis function 1 associated with vertex 1. Consider we have this kind of tetrahedron located at origin. For coefficients of n1, we have the right side value to be 0. Only the value associated with vertex 1 is 1. And the left side are the vertex positions. And by solving this equation, we can get the basis function n1 for vertex 1. And similarly, we can also obtain other basis functions for other vertices. Based on the basis function, we can use the basis function to represent the undeformed and deformed states within the tetrahedron, as shown here. Previously, we know that the deformation gradient can be written as dx bar. So here is the equation to compute deformation gradients for this single tetrahedron. And since we know that the basis function is linear on elements, so based on the formulation of the deformation gradient, we know that this deformation gradient is constant within this linear tetrahedron element. So if we need to compute the element's energy, so we have somehow integrate over the domain for the energy density function. So since this F deformation gradient is constant within the linear tetrahedron element, so basically it's deformation, it's the energy density function times the rest volume. Okay, so we already know how to compute deformation gradients and strain, and also how to get the energy. So we can, but the connection between strain and energy is still missing. So we can use the material model to link the strain and energy. And for linear elastic materials, the stress and strain relationship is linear, and the strain energy density function is quadratic in strain or stress. And this, with the energy density known, we can get its Cauchy stress by taking the derivative of the density function with respect to the strain. And here, this lambda and mu are non-linear parameters corresponding to the material that's we are choosing. And for nonlinear elasticity, we can replace this Cauchy strain with green strain, and we arrive at the Sentinel's kickoff material as here. And this is the energy density function. So based on this, we can compute the energy gradients and Hessian for each element. Then we compute the static equilibrium states by solving Newton's method. Okay, next I will have a brief description of discrete elastic rod model. Discrete elastic model is represented as in this figure. It's basically a discrete center line and adapted frame which describe the orientation of the elastic material around the center line. And its energy can be composed into 3 components: stretching energy, bending energy, and twisting energy. And in the following, I will describe each of them briefly. The stretching energy is simply by the quadratic term of the axial strain, as shown here. And for the bending, similar to the stretching, we basically measure the difference in bending for the rest and the deformed states. And here, this kappa is the material curvature, which measures how large of 2 sequential edge bends in 3D. And twisting is a little bit more complex. In discrete setting, we need to compute the twist difference between 2 sequential edges, that is, twist angle difference. To do this, we start from the parallel transport. And this parallel transport is basically a rotation that gives the minimum rotation between 2 given vectors. And here, I will show how we use the parallel transport to rotate the edge from the rest state to the deformed state based on the 2 given input vectors. And then the basic idea for measuring twisting is for 2 sequential frames, we measure the twisting between them by first parallel transport, the left one to the right one. And from these aligned frames, we can compute the angle difference between these 2 frames, and which is represented as delta theta. And then the twist can be computed as here. And this theta is already degrees freedom associated with each edge. And then, therefore, we can compute the twisting energy by basically measuring the difference between the current twist and the rest twisting. And after we know what of the energy atoms in discrete elastic rods, we can combine them to get the what of the elastic energy, and then we can solve the static equilibrium states by using Newton's method. Okay, with the simulation models, we can use them to forward predict the deformation behavior of materials and the external forces. To characterize the macro properties, we need numerical homogenization. And the metamaterials are generally made from repeating microstructures. The unit cell is the smallest repeating element that defines the entire structure. Instead of simulate the whole piece of material, which would be very expensive, we can analyze just this small representative piece or unit cell to infer the behavior of entire metamaterial. And homogenization is the process of treating the metamaterial as an effective continuous media with averaged properties like stiffness or Poisson's ratio getting from the microscopic structure. And the basic idea is using the native scale or micro scale simulation data to fit the macro mechanic properties. And for this fitting, we first need to know a macro mechanic model that can effectively represent the homogenized material. For this thin shell material, the most interesting feature are the directional stiffness or stretching and bending. And the linear elasticity with quadratic strain energy can be directly applied here. And here we have the epsilon and kappa as the membrane string and the bending string. And this C and B are the material stiffness tensor that we want to fit. And they have symmetric rank 4 tensor with 16 entries. But due to the symmetry, only 6 entries can be independent, even in case of complete anisotropy. And here, based on this strain energy density from the finite elements, we know that the stress can be computed directly by differentiating with respect to membrane and bending strains. And with this micro and macro mechanic model defined, we can now proceed to mapping between the two via homogenization. With macro mechanic model defined, how do we run the simulation to obtain deformation data for a given material pattern? Here are still some problem. First of all, regular simulation does not consider tiling, as you can see here. And how do we apply directional deformations to this kind of material pattern? One way is to use fix some of the vertices and stretch on the other side or somehow. But fixing those positions will artificially stiffen the structure. So we consider periodic tiling of the material as shown here. And the essential idea of homogenization is to subject to a tileable unit cell of material to various boundary conditions that creates different state of deformation, and then we can use them to fit the stiffness tensors. Okay, for periodic tiling, let's first talk about in-plane periodic boundary conditions. For in-plane periodic boundary conditions, basically it requires that pairs of opposite tile boundaries, left and the right top and bottom, should have matched without any gap and overlaps. And for example, we have these two reference position, x alpha and x beta, and we can compute its translation vector dij. So for all of other pairs of vertices belonging to these two opposite boundaries, we ask that one of these pairs should match this translation vector dij. So with in-plane periodic boundary condition defined, how could we deform the material? So the idea is that we can directly change the translation vector that we just defined to deform the tiling. For biaxial deformation, we'll have the principal deformation direction and its orthogonal direction, which are dp and do. And for target deformation in these two directions, which is epsilon p and epsilon o, we can easily stretch the deformation in these two directions and combine them together to get the final translation dij. And this allows us to deform the material with corresponding target strain that we applied. And the deformation of this biaxial deformation can be obtained as here is basically these biaxial strains are basically like the eigenvalues and the direction as eigenvector, so we can reconstruct it by using this one. Or alternatively, we can use the positions on two opposite boundaries to get the deformation gradient. We can deform the material with different directions, and for fitting, we need the material in-plane stiffness tensor. We know that the linear relationship between strain and stress gives this membrane tensor, stiffness tensor. Therefore, to fit this membrane stiffness tensor, we need to compute macroscopic strain and stress for the fitting. As we discussed in finite element methods, the linear cursive strain can be written as this form based on the deformation gradient that we just defined. And to compute the cursive strain, stress tensor, we can use the traction vector relationship to compute its cursive stress tensor, as shown here. And this F are the forces divided by the length of this 2D tiling. And these N are the normal directions of these boundaries. Okay, then we can fit the stiffness tensor, as shown here. And it's more stable to fit its inverse, which is called compliance tensor. And the directional Young's modulus can be obtained by extracting the compliance tensor in specified direction. And here, we can extract the directional Young's modulus from the fitted membrane stiffness tensor. And here, we have this D transpose, which is the uniaxial unit stress. And from the relation that we know here, so stress times the membrane stiffness tensor, we can return the strain. And in order to get the deformation, we still need to times the direction that we want to get. And finally, we can, in the bottom term, we can get the deformation for a given unit stress that we applied. And then the Young's modulus is basically defined the ratio between the applied unit stress and its corresponding induced deformation. And for the Poisson's ratio, the idea is similar. We just need to get the deformation in the orthogonal direction and in the direction that we applied. And the final Poisson's ratio is basically the negative ratio of them. For bending, cylindrical bending is a natural choice since it does not induce Gaussian curvature, which will introduce membrane deformations. So for the bending periodic boundary condition, we decompose the translation, the bar ij in the rest states to the bending direction and its orthogonal direction, which gives us these two orthogonal lengths. And this length, LR, will be mapped to the radial direction of the cylinder. And it can be used to compute the rotation, because we know the length of the cylindrical bending, and it's basically the axial length. So that's with the curvature we know, we can know the angle of the rotation. And we also know the direction of the bending, so we can directly reconstruct this rotation matrix. And this length LA in the axial direction can be used to obtain the Dij by multiplying with the cylindrical bending direction V. So finally, we have this relationship for the cylindrical bending. Okay, we can now fit the bending stiffness tensor. And here we use the energy for the fitting because computing the bending moment is difficult to on the curved patch. And for this fitting, actually we still need a spherical bending data since using cylindrical bending alone will lead to rank deficiency matrix. And the basic idea of spherical bending boundary condition is similar to the one that we described in the planar case. Okay, then I will describe how we extend the numerical homogenization to the discrete interlocking materials. How do we characterize and model the macromechanical behavior of discrete interlocking materials? So in this work, it's inspired by medieval chainmail armor. This interlocking material possesses remarkable flexibility while also demonstrating impressive strength beyond a certain range of deformation. These unique properties make them very attractive in diverse range of applications. And here, you can see more detail of discrete interlocking materials. Unlike conventional elastic materials, the mechanics of discrete interlocking materials is governed by contact between individual elements. And this contact gives rise to deformation constraints and complex coupling for in and out of plane motion. For example, this threefold symmetric channel shows an interesting saddle shape when bent along a given direction. And this torus knot structure allows large cylindrical bending in two orthogonal directions, but prefers spherical bending along its diagonal direction. And this scale material shows different bending limits for positive and negative curvature. While deformation limits are determined by the shape of and elements among the elements, predicting the macromechanic properties of discrete interlocking material from the native structure is still a highly non-trivial task. For example, these two threefold symmetric channels are bent using same uniaxial loading, is indicated in orange. The design A has circular cross-section, while cross-section for design B are slightly ellipsoidal. This small asymmetry in geometry leads to much larger coupling between principal and the orthogonal curvature as shown in blue. Furthermore, the rigid movements of discrete interlocking material lead to kinematic deformation, no elastic deformation for individual elements at all. And this completely different from the traditional homogenization framework, and which is used to characterize the elastic properties. So in this work, we introduced a computational approach for modeling and characterizing discrete interlocking materials composed of quasi-rigid elements. And this method built on three main components. First, native scale simulation model, that's to predict the behavior of interlocking materials and the external forces or boundary conditions. Based on that, we can then characterize discrete interlocking materials while hundreds or thousands of deformation tests on native scale simulation. And from that, we can generate strength space representation, which is called deformation limits, which is the maximum deformation. And with this, we use the constructed strength space representation to drive the macro scale simulation model, which we use a thin shell here to mimic the deformation of the native scale simulation. So for the native scale model, we can use static equilibrium states to get the states for rigid bodies with contacts by solving this unconstrained minimization problem as we described before. To characterize the in-plane behavior of DIM, we still need a tileable unit cell as shown here. For the translation vector Tij, it's described as before, but we still need to somehow constrain the rotation between two opposite boundaries so that this rotation should be identical. After defining how to apply in-plane deformations, here we analyze deformation limits for bending. We initially consider using periodic boundary conditions analogous to the planar setting, but the single curvature states can be conveniently modeled in the way that we described just now. The concept of periodic boundary condition does not really extend to doubly curved setting, because one cannot, in Euclidean geometry, define a finite-sized double curvature patch that tells with itself. However, finite patch of discrete interlocking materials can genuinely exhibit state of double curvature. So some material will even strongly resist uniaxial bending and prefer negative Gaussian curvature instead. For example, this threefold symmetric channel as shown here, it shows a saddle shape when we bend it along a given direction. And for this reason, we use circular finite patch of paraboloid surface defined here to bend interlocking materials. So basically, we can directly represent center position of elements by paraboloid equation here. Okay, so we can then deform the structure to obtain the mechanical properties of the material. But unlike elastic materials, discrete interlocking materials can freely deform in a given direction until a hard stop due to tight contact between elements to prevent further deformation. So instead of deriving elastic properties, we derive deformation limits of the materials. So, and we observe that discrete interlocking materials can be fully described by enumerating all feasible macroscopic deformation. And therefore, for each material, we perform a lot of virtual deformation tests for uni and backsaw stretching and bending in different directions. And strain for in-plane and out-plane are symmetric 2x2 matrix, and they are, can be represented in 3D strain space. The deformation boundary can be constructed as closed and watertight meshes for stretching and bending, as shown here. So based on these strain space boundaries, we define high-level directional deformation limits for characterizing these discrete interlocking materials. To enable efficient preview of discrete interlocking materials with large number of elements, we also developed a macro-scale model that combines the thin shell simulation with homogenized deformation constraints. To this end, we interpret per triangle strain and curvature tensor as points in three-dimensional strain space. And then we enforce deformation limits through soft constraint function that penalize the motion points in the strain space outside the stretching and bending boundary. And here is the implicit Euler simulation result for the threefold symmetric material. And we can see the macro scale simulation returns a close result to the native scale simulation. And here are some results. The first example is a hexagonal pattern in which each element connects to its 6 immediate neighbors, leading to an overall threefold symmetric structure. The autoplane profile for this material are almost isotropic as shown in this animation. However, the difference in sign between principal and orthogonal limits suggests an interesting behavior when applying uniaxial bending in any given direction. The material will bend with opposite curvature in orthogonal direction, leading to this characteristic saddle shape. And here's the comparison of the macro scale simulation results with native scale simulations and the deformations observed in physical prototypes. And all of them are aligned very well with the physical prototypes. And the second example is a four-fold symmetric material consisting of torus node elements arranged in a regular quadrilateral grid. And this material exhibits very large bending deformation in 10 and 100 degrees, but much tighter threshold in 45 degrees. And this behavior can be identified in the strain space boundary for bending because it shows star-shaped protrusion, and this shows that the bending in 45 degrees gives much tighter threshold, and in 0 and 100 degrees it shows very large bending as shown here. Finally, in this example, the method can be applied to elements with more complex geometry. And here the elements consist of six-fold symmetric base with hexagonal plates on top of one side. And the macro scale simulation results can remain closely track the behavior observed in both native scale simulation and physical prototypes. The asymmetry in the shape of this scale mail translates into an asymmetric bending behavior. As can be shown in this example, in one direction, the bending limit is determined through contact between the interlocking rings and the base. In the opposite direction, contact between scale and elements puts a much earlier stop to bending. Okay, so we have talked about numerical homogenization for elastic materials, and how does it extend to characterize the kinematic deformation limits for discrete interlocking materials. And here comes to the question of how to inverse design metamaterial with desired macro mechanic properties. So I will describe it as the next step. And so we can have a maybe 5 minutes break first. Yeah. Okay, so in this step, I will describe the numerical method in the inverse design. So for the inverse design, inverse problem is general is very general in computational design. I will start by showing how we do the inverse design with a simple 2D elastic bar. After that, we can see how could we apply this method to inverse design of metamaterials. So in the fourth problem, let's consider a 2D elastic bar as shown here. So we have its undeformed state P, and its external force, which is the gravity in this case. And after deformation, we can get its deformed state X, as shown here. So in this fourth problem, given design parameters P and external force Fx, we compute its static equilibrium configuration X by solving this force balancing equation. So if we change the undeformed state P, it will give corresponding change in the equilibrium state X. And how can we determine design parameters P that lead to a desired equilibrium state? And here our target is its undeformed state is this horizontal bar. So in order to do this, we first need an objective function to quantify the distance between currents and the deformed configuration to the target. And here the objective function is basically the squared norm between the current deformed state and the target one that we want. And we want to find the X that minimizes T for given design parameters P. And here we have one more constraint need to be satisfied, which is the static equilibrium state by solving this force balancing equation F equals to 0. So the formal formulation is like this. This is the state before optimization. And after solving this inverse design problem, we can achieve the rate state as shown here. The interpretation for this constraint for this formulation is for all possible equilibrium states X computed from parameter P with this F equals to 0, we find the one that minimizes this objective function. And here is a more general optimization problem. We have the unknown variables X and its corresponding objective function and constraint. And the question is, how can we solve this optimization problem? So there are lots of numerical methods in inverse design, for example, sequential programming, sensitivity analysis, interior point methods, augmented Lagrangian method. And today I will only cover sequential quadratic programming and sensitivity analysis. One common way to solve optimization problem is to construct the so-called Lagrangian, which is sum of objective function and the weighted sum of the constraints. And the weights here are the Lagrangian multipliers lambda. And we have the deformed positions X, undeformed positions P, and the Lagrangian multipliers lambda. These are the degrees of freedom that we need to solve. And we stack them together as S. So we will have 3 times D times N number of degrees of freedom to be solved. So in this case, we solve a 2D elastic bar, so this D equals to 2 So finally, we arrive at 6 times n degrees of freedom that need to be solved. So we solve this problem by looking at the first order optimality condition. It tells us that the gradient of the Lagrangian vanishes for all variables. And the Lagrangian with respect to lambda returns us the constraint. That's what we want. The constraints have to be satisfied. And for the gradient of the Lagrangian with respect to x, this equation asks the objective gradient must to be in the span of strain gradients, or they must be collinear. Why? Because if we assume that we are at the optimum, if they are not collinear, they must be a direction that we can go to decrease the objective value and does not violate the constraint. So this condition must to be satisfied. And it's similar for the Lagrangian gradients with respect to the design parameter P. So for a given S that does not satisfy the optimality condition, then we look for a delta S that's such that it comes to 0. So from Taylor expansion, we solve a linear equation to get this delta S. And here I write all of the term here. And to compute this left side matrix, we need to compute some of third order tensor, which are this fourth term, this one. So they are third order tensor. Additionally, this matrix in most cases will be indefinite matrix. One good way to solve this is using QP solver, for example, Mosaic or Groovy. And basically, we can just feed all of the things to solve this in Mosaic and Groovy. It's very convenient. Okay, after solving this linear system, we can obtain the search direction delta S. But the new S still will not make the gradient of the Lagrangian be 0. So the idea is to iterate by Newton's method. And one problem here might be how to find a good function to measure the progress of the optimization. So here we use the merit function, which balances the progress of the objective function and the constraint. And here we use L1 merit function as example. It's basically sum of the objective gradients plus the L1 norm of the constraints multiplied by a lambda, which is related to the Lagrangian multipliers. So SQP is a powerful optimization method, and it can be very fast. Hessian of this Lagrangian involves high-order derivatives, and it will be very difficult and expensive to compute, and it's always introduced indefiniteness. And alternatively, we can use Cauchy-Newton method to approximate this Hessian and directly solve the linear equation and get the delta S. And SQP, as we remember, it gives us, for this 2D elastic bar, we have 6n degrees of freedom need to be solved. So it leads to a very large number of variables. Another way to solve the problem is called sensitivity analysis. Recall that for a given design parameter P, we run simulation to obtain equilibrium state X. And for design, we need the design objective gradients. And based on the chain rule, we get the dt, dp as the following form: dt, dx, dx, dp plus dt, dp. And here, this dt, dx, and dt, dp are very easy to compute. And the only thing left is dx, dp. And how do we compute this dx, dp? Because we basically run a simulation for the inputs design parameter P, and finally we arrive the static equilibrium state X. And what we basically do for the simulation map is we solve a force balance equation, which is F equals to 0, and this is always true. So for any change in design parameters P should lead to a corresponding change in state X, such that this F equals to 0 is always satisfied. So that tells us that this dF dP should equals to 0. And then based on the chain rule, we can get this right side equation, dF dx dP plus dF dP equals to 0. And this is the equation that we can solve. And then we arrive at the sensitivity matrix dxdp equals to the right side form by solving the linear system. So we finally can get this design objective gradient, and we can solve this problem by using gradient descent or LBFGS. And here I use gradient descent as an example. So we first compute the search direction, which is the negative of the design objective gradient. And for the line search, we first update the design parameters P. And then with the new design parameters, we do the simulation to get its corresponding static equilibrium X. And then we can evaluate the objective function. If it's smaller than the previous objective, then we can go to the next iteration. During the computation of design objective, we always have to compute a linear system to get the final gradient. If the number of state variables X and design parameters P are large, it will be very expensive to compute dxdp for each iteration. You basically have to solve multiple linear systems. So one trick here, we can accelerate the computation speed of design objective gradient is called the adjoint method. So instead of, we could avoid computing dxdp explicitly. We compute this blue left side in the design objective gradient first, and introduce the adjoint vector lambda as here. Then we basically only need to solve one linear system because this dt dx is just a vector. So finally, we can use this adjoint vector to compute the objective gradient. Okay, so we just covered the SQP and the sensitivity analysis to solve a constraint optimization problem. For the inverse design of metamaterial, we have a similar forward problem, F equals to 0. So with the inputs mechanic properties, such as Young's modulus and the Poisson's ratio, we can optimize or generate the corresponding structures. Then in this case, we optimize directional Young's modulus to the orange target values. We can introduce the objective function that minimizes the difference of the Young's modulus. And finally, we can achieve the optimized structure as shown here. Okay, then I will talk about two papers of inverse design of metamaterials based on the theory that we just learned. So I will first describe my recent work, inverse design of discrete interlocking materials with desired mechanical behavior. So after we know how to characterize the macromechanical properties of discrete interlocking materials, it comes to the question how to inverse design discrete interlocking materials with desired kinematic deformation limit. So for given targets, the basic idea is that we still do the simulation and then we use constraint optimization to do that. But there are still some problems need to be solved. First of all, directly use explicit triangle mesh as before will be very computational expensive. And another problem actually in the IPC, also called incremental potential contact, is that incremental potential relies on a superposition of smoothly clamped contribution from a set of active primitive. And for here, the contact potential energy of a vertex with edge will change from 1 to 2 and 2 to 1. And this will introduce contact energy peak as segment junction, as shown in the left side plot. So basically, if a point move from left to right, is basically change from 1 to 2, and so it will give this kind of energy peak. And in our case, it will impede the free sliding of the interlocking elements during the optimization. So the problem will slow the convergence of forward and inverse problems. So therefore, in this work, the idea is instead of using piecewise linear triangle meshes for interlocking elements, we use union of smooth parametric torus to implicit represent interlocking elements. This implicit representation allows to simulate discrete interlocking materials with smoothly involving contact. And the contact potential requires the distance for two tori with the given rigid transformation Q. We compute it by solving a minimization problem for vertices belonging to different tori, as shown here. So basically, we are optimizing the parametric coordinates Cij, which C is the parametric coordinates in these two tori. So using this implicit representation, we still need to address some singularity problems. When two interlocking tori rotate relative to one another, we observe that a shift in the number of contact pairs from 1 to 2 or from 2 to 1, with each of them starting or ending with the squared distance smaller than the contact activating distance, which is d hat. As can be seen here, a second contact pair suddenly appears or disappears during relative rotation between the tori. And if candidate step lead to such kind of change in contact pairs, the contact energy abruptly change, and the step during the line search will likely be rejected. So our key observation is that the smallest eigenvalue of the discrete of the distance Hessian increases smoothly from 0 with the appearance of the contact pair in the contact set. And this allows us to introduce a smooth factor to compute a continuous and differentiable energy for the contact. Then we have our revised contact potential by adding this smooth factor S. Then we can compute static equilibrium states by solving this form again. And one thing different from before is that we are now dealing with implicit representation instead of explicit triangle meshes. And the continuous collision detection for triangle mesh does not apply here, so we somehow need to adjust. So similar to the distance computation, we solve this minimization problem again to this kind of minimization problem to obtain the maximum intersection-free step size. So if we obtain the distance, basically if a two tori during CCD, we compute the distance. And if this distance is smaller than a very small threshold, which is as contact, for example, its value corresponding to 1 to the power of -20, then we treat it as contact. Then we will shrink this alpha high, which is the maximum step size, by 0.9 until we find a distance that is larger than the threshold, so that we can find the distance between two tori is larger, and without any intersection. So basically, for the inverse design of deformation limits, it comes to, for the in-plane, we have the objective function. So basically, it measures the difference between the deformations of the current one and the target one. And we also have to solve static equilibrium, which is f equals to 0 for all direction that we want to apply. And we also need to have constraints, which basically tell us that the cross-section of one tori should be smaller than the whole of its neighboring tori. And we also have the bound constraint for design parameters. So that allows us to have the design parameters within a printable range. And similarly, we can also define our out-of-plane objective function as here. And with this optimization formulation defined, we can solve it by using SQP. So here is the result for the structure before and after optimization. The uniaxial deformation limits are optimized to isotropic from this kind of star-like shape here. And it's optimized to this isotropic blue profile. And it has been optimized more or less like twice as large as before. But if you take a look at the appearance of the interlocking material, they are pretty much very similar to each other. And this one we optimize to an anisotropic profile from the same start initial gas. And this leading to obvious heterogeneous elements distribution. And for out-of-plane bending, we can fit the material with orthogonal bending deformation limits like this one and this one. And our method can also apply to other kind of elements. For example, this four-fold symmetric material and the basic CML. Okay, and I also like to talk about another paper that's from Juan Montes, who was expected to deliver this course together with me, but there was some problem, so he could not come. And but I found this research is very interesting and would like to have a brief description of it. In graphics community, we have developed powerful algorithm capable of computing texture of stripe patterns on arbitrary surfaces. One area that hasn't been fully explored is the ability to control the macro-mechanic behavior of structured surfaces. In this regard, stripe patterns provide an interesting design space for biomaterial structure. By 3D printing striped shape pattern on textiles, the created material can exhibit quasi-extensible in one direction while being compliant in its orthogonal direction. By varying the design of the stripe pattern, it allows us to change the overall response of the structure when subject to external forces. Controlling this space allows us to create structures with prescribed macro-mechanic behavior. In order to achieve this goal, this paper proposed a gradient-based optimization framework that synthesizes stripe patterns on a surface that best fits a given macro-mechanic target. For each iteration, given a candidate's vector field, we can first synthesize a stripe pattern design and evaluate its performance against an objective target through numerical simulation. And this simulation problem requires the computation of gradients, and most importantly, the derivative of stripe pattern design with respect to the design parameters. And the derivatives of the predicted equilibrium states obtained through physical simulation with respect to the stripe pattern. For the generation of stripe pattern, this work is built by Knoppy et al. For generating stripe pattern on a triangle mesh. Given a vector field P, we find a phase function V that's increased as uniform as possible along a given direction described by the vector field. These phases are represented as complex numbers with real and imaginary components AI and BI, whose values are expressed as a periodic function on the unit circle. These phases are found by minimizing an energy that's measured how well the phases integrates the vector field. This energy has multiple minimum, including the trivial solution V equals to 0, so which can be avoided by imposing a constraint of its length. The optimal condition for this energy minimization problem is to a generalized eigenvalue problem, from which we obtain a non-trivial global minimizer in the smallest energy eigenvector. Once we solve for the eigenvector, we need to transform these phases into a distance function where the boundaries of straps are determined by its zero level set. Thus, by changing the vector field, we can change the design of the strap pattern, given us a clear path in computing derivatives of strap patterns with respect to the vector field. However, the eigenvector that's global minimizes the strap energy is not unique, and for each vector field, we have an infinity of phase function that's equally minimize the strap energy. This null space manifests as multiplicity of two eigenspace that visually looks as a shift of pattern in the direction orthogonal to the straps. Due to this null space, derivatives are not well defined, which is an issue for gradient-based optimization. So they basically address this issue by constraining the eigenspace on the original energy formulation. So if we look close at the problem, the null space corresponding to synchronous rotation of the phase function applied per vertex. So if we rotate phase by 90 degrees, we obtain a negative image of the orange pattern. So in order to obtain a unique eigenvector per vector field, it's suffices to pick any of the nodal phases and constrain it to have a fixed value. A simple choice is just to constrain its imaginary component to 0 by means of the linear constraint mu times bk, where this mu is an additional Lagrange multiplier. Well, this approach solves this differentiability problem, but it will lose a large region of design space, while all these eigenvectors have same strap energy, and the influence to these mechanical properties of the structure is different. So this can be actually recovered by introducing an additional degrees of freedom theta, which rotates the eigenvector in the eigenspace using two orthogonal eigenvectors as the basis, which span the whole eigenspace again. And finally, we can find the sensitivities of the eigenvector with respect to the vector field from the KKT system with the additional constraint. These strapped patterned structures are made of two materials, one soft and one stiff. The interface between the two materials changes as the design of strap pattern changes. Proper treatment of this interface is important, since both materials deform at different rates when subject to an external force. To accurately simulate the behavior of a design, we must model the discontinuity in the strain across the interface of the materials. To this end, we can discretize the structure using solid shells, which basically we obtain by extruding the mid-surface of the structure given by triangle mesh along its normal, resulting in prismatic elements in 6 nodes and the bilinear shape functions interpolating the space. To model the discontinuity at the interface between two materials, we use XFEM. By interpolating the straps level sets using the shape functions of the prismatic element, we introduce new shape functions and the new degrees of freedom, also known as enrichment, that introduce a discontinuity at the location of the interface. This enrichment allows us to model the jump in strain across the interface without need for conforming remeshing. And this formulation gives us an explicit dependence of the equilibrium configuration with respect to the level set of the strap phi, from which we can compute the derivatives. And here are some results. In this example, we test the ability of the framework to modulate the stiffness of a periodic textile patch using straps. Starting from concentric circles in the left, we ask for different stiffness profiles, obtain isotropic, orthotropic, and tetragonal behavior. And in this example, we use the method to design variable stiffness material as a design target. Starting from parallel straps, we ask that displacements vary linearly when applying a constant horizontal force, such as to encourage a stiff and stiff to soft distribution from top to bottom of the structure. And here we show that the differentiable strap pattern can likewise be used to drive large out-of-plane deformation upon actuation. Starting from the parallel strap design, we optimize the pattern so that the flaps of the sheet fold when pulled along its horizontal axis to grip on object. We show that the optimized pattern outperformed the initial guess by achieving large deformation by pulling both design using the same force. And this method can also combine with other means of actuation to produce large controlled deformation. And we demonstrate this ability by designing a pneumatic actuator that's deformed in a quasi-circular shape. While this framework was originally designed for biomaterial distribution, we can also use them to improve the stiffness of the structure by controlling its geometry. And in this example, we can optimize for the pattern such as to minimize the compliance of the vase and the vertical load. And for the unoptimized design, the buckle, it's very easy to buckle and the force of 45 Newton. In contrast, this optimized design can withstand 90 Newton while experiencing less deformation. So to wrap up today, I have talked about what is metamaterials and the design challenges, then described several computational models to forward predict the behaviors, and we can use numerical homogenization to characterize the macromechanic properties. I also showed how do we extend the method to characterize and model the macromechanic properties of discrete interlocking materials. After that, I also showed the numerical methods such as SQP and sensitivity analysis for the inverse design. Finally, I talked about two recent research for the inverse design of metamaterials. And for outlook of metamaterial design, now we are in the AI era. Machine learning techniques already present good performance for the design of metamaterials. For example, here is the work leveraging the neural network to encode nonlinear mechanics of an entire family of isohydrotilene metamaterials. Additionally, generative AI already shows its powerful performance for image and video generation. Here are also a lot of work leveraging generative AI for the designing of metamaterials. For example, in our recent work, we present a novel generative model that integrates latent diffusion with a hybrid neural representation to generate diverse categories of microstructures with desired macromechanic properties. This generative model can also allow for design of heterogeneous distribution that exhibits specific deformation behavior. Leveraging machine learning algorithm and generative AI for designing new metamaterials would be a very interesting direction for future research. In addition, large language model is also a powerful tool in many fields. So how to leverage the reasoning ability for large language model to design metamaterials with new structures would also be a very interesting direction for future research. Okay, finally, I would like to first thank Professor Ben Bickel for all his support to make this course happen. And I would also like to thank Professor Bernhard Tomasewski and the Stellan Chorus for the support of these works. And here are some references. And with this, I would like to thank you for listening and get some questions from you. Thank you. Yeah.
So with the textiles, you had the distribution of stiff material and non-stiff material. I assume that using some kind of manufacturing process like 3D printing on fabric, you can get a gradient of stiffness on these materials. Is that something you have considered?
You mean get the stiffness of this kind of bi-materials?
Yeah, not just binary, but maybe having different number of layers to get different levels of stiffness at different points.
Ah, okay. Yeah, that's a very good point. And we didn't actually try that, but that's a very good point and a very interesting direction. Yeah. Yeah.
Thank you very much for a very nice talk. I was wondering, in this optimization process for the predefined behavior of the material, it looked like you started with something symmetric, with these parallel lines, and also the shape seemed symmetric, and the required behavior seemed like symmetric, but then the optimized pattern did not have these symmetries, which surprised me a bit. So I was wondering, like, are the symmetries to be expected, or did I miss something and the problem is not symmetric, or?
Oh, okay. Maybe I can.
Like in this where you have these parallel strips, and then you pull in like X direction and it bends in Y direction. And I thought that the optimized pattern would have some symmetry back to X, Y axis.
You mean
Yeah, like
this one?
For example, yeah.
For this one, it should be symmetric, right? For the left one. But for the right one, because we optimize to a heterogeneous distribution, so it will not be symmetric. And since we use simulation and numerical homogenization to somehow characterize the macromechanic properties, so simulation might introduce some little bit instability or the threshold for the convergence. So that might introduce a little bit asymmetry into the homogenized results. That is possible, yeah. Any more questions? Okay, if no, yeah, I would like to thank you for listening.